So this is Dr. Kavita Singh, Associate Professor in Department of Civil Engineering and Institute of Aeronautical Engineering. So today our topic will be for discussion will be satellite sensors. So in the previous lecture we have just discussed about the different types of satellites, their resolutions, and that all resolutions depend on the type of the sensor. So while designing the sensor, the engineer has to see about the types of resolution should be designed properly at the time of the designing process itself. So what type of sensors are there and what type of sensors are used in which type of spectral bands, like in the spectral reflectance, we will see the curves and all. So what type of sensors are used in different bands of our electromagnetic spectrum that we will see today. So let us discuss this topic today. So topic is satellite sensors, and the topics which we are going to cover in this whole lecture is about sensors, imaging sensor systems, multispectral imaging sensor, thermal sensor, microwave sensor. So these will be the different types of sensors which are used in the different fields of electromagnetic spectrum. So what is a sensor? Basically, sensor is used by the remote sensing process. So the remote sensing process, if we remember, we have discussed in the previous lecture that there are two types of remote sensing. That is active remote sensing, another one is passive remote sensing. So passive remote sensing and active remote sensing, both the remote sensing is having a sensor which is attached to the satellites. So in passive, the electromagnetic radiations are required for the capturing the information. So whenever the sun is available, then only the passive remote sensing will work. So the sensor, at the time of the designing of the sensor, it should be designed in such a way that it should only work when the passive light is available. That means whenever the sunlight is available, right? So these sensors are passive remote sensing, either recorded by the reflected, emitted, visible, thermal, microwave regions, and active. When an engineer will design a sensor, then the sensor should be in an active way, like the sensor should be able to work in 24 hours conditions, like weather conditions, whenever it is not favorable also. This active sensor should work. So the active sensors is like microwave sensors are always comes under active sensors, whereas passive sensors, we will see these sensors will only work whenever the sunlight is available, right? So sensor systems means we have classification of sensor system here. So we have multispectral sensor system, and we have thermal sensing system, microwave and radar system. We have three types of sensor systems here. So multispectral, again if we go forward, we have photographic system, scanning system, and next we go to thermal sensing system, and next we go to microwave and radar system. So let us understand what are these all types of sensors we go through. So imaging sensor system, various components of sensor system operating in the visible, infrared, thermal and microwave regions of the electromagnetic spectrum. So useful wavelengths are mostly in the visible and infrared for passive remote sensing detectors, and in the radar and microwave region for active type of sensor. So all the imaging sensor systems are classified based on the technical components. So they are based on the technical components that are classified, and the system and the capability of the detection by which the energy is reflected by the terrain features and is recorded. This classification scheme is multispectral imaging sensor system, thermal remote sensing system and microwave radar sensing system. So it is basically classified based on the reflected energy of the terrain features. Terrain features means all the geographical features which are on the earth surface. How do they reflect and how it is recorded to the sensors, and how it is given in the form of output by the sensors. So here we have three types here: multispectral imaging system, thermal remote sensing system, microwave radar systems. So these all systems will work in a different regions of electromagnetic spectrum. So what is electromagnetic spectrum? If you remember, we have discussed long back in the lectures of electromagnetic spectrum. So electromagnetic spectrum is divided into different regions, like we have here short wavelength region, short wavelength, then we have visible region, visible region, and then we have long wavelength region. Okay, so when you talk about multispectral imaging system, thermal remote sensing system, microwave remote sensing system, so these all three will not at all work in the short wavelength region, because this short wavelength region is before visible. It's like ultraviolet region, gamma region, X-ray region. So in this region, the radiation is totally absorbed. Totally absorbed. So radiation is totally absorbed. So it is totally waste for the remote sensing process. So in this region, the remote sensing process will not work. So sensor is not designed for this region. The sensor is designed for the visible region and long wavelength regions. Okay. So visible region means this visible region sensor will be passive. Passive sensor will be designed for the visible region, because from the visible region itself the electromagnetic radiation can pass through, and the sensor can detect the objects or detect the terrain features on the earth surface in this region itself in the presence of sunlight. Okay, in the presence of sunlight itself it will just capture the information. Now we come to the long wavelength region. This long wavelength region is a region where you find this radar region, radar, microwave, and you have thermal. So thermal region, so these are all regions which is beyond the visible region. So beyond the visible region, we have infrared region, we have thermal region, then microwave region, then radar region. So this thermal, multispectral, thermal and microwave, these all three types of classification and three types of sensors will work only in the visible portion of the spectrum and only in the long wavelength region of the spectrum. So then let us understand what is multispectral imaging sensor and what does it do, how it works, and how the way the images are collected. Okay, so multispectral imaging sensor system. In case of multiband photographic system, different parts of spectrum are sensed with different film filters combination, and multiband digital camera images and video images are also typically exposed on the camera sensor through the different filters. So electro-optical sensors such as thematic mapper, Landsat typically sense at least several bands of electromagnetic spectrum. Multispectral means yesterday itself or previous lecture itself we have just discussed about the resolutions. So in the resolutions, if you remember, we have just discussed about different resolution like spatial, spectral, radiometric, and temporal. Okay, so in the temporal, in the spectral resolution, we have just discussed about the different bands. Like we have different band combination: band 1, band 2, and band 3 or band 4. So the satellite imagery with having a resolution, a high resolution, high spectral resolution, gives the information in 3 band and 4 band, right? So this 4 band information is given in the multispectral bands. Multispectral band means not in a single band, like it will be in the red band, blue band, green band, or infrared band. Okay, red band, blue band, green band, and infrared band. So these 3 or 4 bands the information will be given, or else the information will go in the let us say infrared band, microwave band. So different regions it will take the information. That's why it is called as multispectral imaging sensor system. So it is having a capability of capturing the information in multi bands. Okay, so this is how it works. So it is having a information of different types of bands again. Now, two types of multi-spectral imaging sensor systems we have here. So one is the photographic system and a multispectral scanner. So photographic system suffers from one major defect considerable considerable distortion at the edges. This is due to large lens opening. So this photographic system will be majorly it will be having some defect, and this is photographic system lens is used in the aerial photogrammetry. So it is having a distortion problem because of the large opening of the lens. Now if you talk about the multispectral scanner, operate on the same principle of the sensing in the multiple spectral bands, but such instruments can sense in many more bands and over a greater range of electromagnetic spectrum. So here it is written, you will see, can sense in many more bands and over a greater range of electromagnetic spectrum. So multispectral images are acquired by means of two basic processes, across track and along track. So it has two types of scanner, multispectral scanner. One is across the track scanner, one is along the track scanner. Okay. So what is across the track and what is along the track? These are two types of scanning system. At the time of the capturing the information, this multispectral scanner will work in two different ways, either across the track, either along the track of the terrain for the swath beneath the platform. So I hope you remember what is a swath. Swath is the path given by the satellite, which it is viewed by the satellite, and it will go in a path called as swath. So this much area to be collected is called as swath. Okay, so it will go beneath the platform. So second type of multispectral scanning system is along the track scanning system. So we have this two, along the track and across the track. So what is along the track scanning? We'll see here. So suppose this is the swath, this is the path. So and this is the fixed sensor over here. So when the sensor will scan, it has to scan in this manner. So it will go along the track. So suppose this is the track, it will go along the track. Now along the track or push broom scanning. We generally call it as even a push broom scanning. That means it is going like a push broom and it is scanning along the track like this or like this, depending on the satellite sensor, how it is moving up and down or up. So based on that, that sensor will be moving. Now across the track here, very clearly we can see, across the track scanners scan the earth in a series of lines. The lines are oriented perpendicular to the direction of motion, the sensor platform. Each line is scanned from one side of the sensor to the other using a rotating mirror. As the platform moves forward over the earth's successive scans built a two-dimensional image of the earth's surface. Now here in the along the track, what we have seen here is swath is like this. This is the swath and the track will be like this. While scanning, it will go in this manner. Okay. Now when we talk about the across the track, so suppose this is the our area to be covered. So how it will go, suppose these are the scan lines. So it will just cover like this portion, it will go like this, across, okay, like this or like this, whereas along in this manner. So this will go in horizontal manner, this will go in the vertical manner, up and down. Okay, so this is the difference between across this track and along the track, and it will capture the information of the earth's surface with these two features. Now multispectral imaging sensor. Now here also we have, it's very clear, whisk broom type imaging instrument, and the B is the push broom type imaging instrument. Okay, so whisk broom, this across the track scanner is also known as whisk broom. Okay, whereas the along the track is known as push broom. Okay, so this is push broom, this is push broom, and this is whisk broom. Okay, so these are the two types of multispectral scanning system. Now across the track scanners can scan the earth in series of lines, and the lines are oriented perpendicular to the direction of the motion of the sensor platform, and that is across the swath. So each line is scanned from one side of the sensor to the other side using a rotating mirror. So one side and the other side means just it is crossing like this. Okay, as the successive scan built up two-dimensional image of the Earth's surface. So the incoming reflected or emitted radiation is separated into several spectral components are detected independently. Now across the track bank of internal detectors, each sensitive to the specific range of wavelengths, detects of the measures of the energy for each spectral band, and then as the electrical signal they are converted into digital data recorded for subsequent computer processing. This is how it works. It will be, the mirror will be rotating, so scanning like this, like this, like this. Again it will come back, scanning in this manner. Again it will go back, scanning in this manner. Okay, like this it will go up and down. Now we have across track scanners. So the IFOB of the sensor and the altitude of the platform determine the ground resolution cell viewed and the spatial. This is the spatial resolution. The angular field of view is the sweep of the mirror, measures the in degrees and used in the record scan lines and determines the width of the image swath. So airborne scanners typically sweep large angles and between 90 degrees to 120 degrees, while satellites, because of their higher altitude, need only to sweep fairly small angles, 10 to 20 degrees, to cover a broad region. So because of the distance of the sensor to target increases towards the edges of swath, the ground resolution cell also became larger and introduced geometric distortions to the images. So the length of the time the IFOV sees a ground resolution and cell as rotating mirror scans called as the dwell time, and is generally quite short and influences the design of the spatial, spectral and radiometric resolutions of the sensor. Now along the track scanners also use a forward motion of the platform to record successive scan lines and build up a two-dimensional image perpendicular to the flight direction. However, instead of scanning the scanning mirror, they use a linear array detectors located at the focal plane of the image, and it is formed by the lens system, which are pushed along in the flight track direction. So these systems are also referred to as a push broom scanners, as the motion of the detector array is analogous and to uh, bristles of a broom being pushed along a floor. So here, same picture, I mean in a different way. So each individual detector measures the energy of a single ground resolution, and thus the size of IFOV of the detectors determine the spatial resolution of the system. Now, along the track, scanners with linear arrays have several advantages over the across track mirror scanners. So, along the track, scanners will be having some advantages like the increased dwell time also facilitates smaller IFOVs and narrower bandwidths for each detector. Thus, finer spatial and spectral resolution can be achieved without impacting the radiometric resolution. So, what is the advantage with the along the track over the across the track is it increase the dwell time, and it also has facilitates smaller IFOVs and narrower bandwidths for the each detector. So the finer spatial resolution and the spectral resolution can be achieved by this kind of scanners. So it will not impact the radiometric resolution. More finely, we can just achieve the uh, higher spatial resolution and spectral resolution from this type of scanners. So because detectors are usually solid state microelectrode devices, they are generally smaller, lighter, require less power and are more reliable and last longer because they have no moving parts. Next, coming to the thermal sensing systems. So thermal sensing system, these type of scanners will only work in the thermal portion of the electromagnetic spectrum. So in electromagnetic spectrum, there is a thermal portion after the visible region. So if this is the visible region, next we have infrared, then we have thermal. Okay, so thermal region, then further microwave, then we have radio. So like that, so on it will go on. So in only the thermal portion of this region, this sensor will work. The sensor will work only in the thermal portion of this region, because it's made for the thermal sensing. It will sense the thermal information on the ground surface, wherever the heat is available, wherever the thermal information is required. This sensor can be used for the getting the information. Like forest fires and all, we can just get the information in this type of regions. And the operation and efficiency of this type of scanning systems are based on characteristics of the detectors. So quantum or photon detectors are typically used to detect the thermal radiation. Now, thermal sensing system, these detectors operate on the principle of direct interaction between photons of radiation incident on them and the energy level of electrical charge carries within the detector and material. Now, these are the different types of material here, like mercury doped, germanium, indium antimonide, mercury cadmium telluride. So, these are all useful spectral ranges 3 to 14, 3 to 5. So if you want to detect these all types of material, it can be detected with the help of this thermal sensing system. So thermal sensor can detect these all type of uh, features on the earth surface. Now microwave remote sensing system. So the region which of the spectrum composed of electromagnetic radiation with wavelength between 1 mm to 1 meter is called as microwave band. So where will be the microwave located in the spectrum? So short wavelength, visible, then we have IR, then we have thermal IR, okay. Then after we'll be having a microwave region, okay. So sensor, microwave sensor is having all weather capability. It can work in all weather conditions. So like radar is the example of this microwave sensor. So it will sense all the information in all weather condition. If it is raining, if it is sunny, if it is cloudy. So any type of condition this microwave sensors can work. So the microwave band is valuable region for remote sensing in view of two distinctive features. Microwave are capable of penetrating the atmosphere. As I said, it is having the capability of getting the information in all weather conditions. So it is having a capability of penetrating the atmosphere under almost all conditions. Depending on the wavelengths involved, microwave energy can see through haze, light rain, snow, clouds, smoke. So whenever these all condition occurs, so these microwave remote sensing will help. So this all information of the all the developmental activities, all type of activities, any day condition. So the all information we get through this microwave sensors only. So microwave sensors are the active sensor. It will work 24 hours. It is having all day weather capability. So it will give any type of information anytime required. So microwave reflections or emissions from earth materials bear no direct relationship to their counterparts in the visible or thermal portions of the spectrum. Now, remote sensing techniques in the microwave region of the electromagnetic spectrum can be classified into two categories. So, active microwave remote sensing, example side-looking airborne radar. So, SLARV is the good example for this microwave remote sensing, and it is a active remote sensor. Passive microwave remote sensing is the radiometers are the examples, right? So, these are the few references for the today's lecture. Like if you want to go through the more content, you can just go through this MNG Ready Remote Sensing NGISBS publication, New Delhi 4th edition. Just go through once. So 4th edition will give you the more information about the sensors and the information about the different types of imaging system, and you can just go through this NPTEL links for the more information about the satellite sensors and fundamental of remote sensing. If you want to know about more about remote sensing process, you can just go through these all books. So these are the few of the references we can just go through to get the more content about it. So I hope you understood about the sensors. We have generally three types of sensors: multispectral, and we have thermal, we have microwave sensors. So these sensors will work based on the their capability and based on their design process, and these are designed for these type of working system itself, whichever band requirement is there, based on that these sensors are designed. So that's all for today. Thank you.
Like, share, and subscribe. Hit the bell icon for more updates.